Okay, so I've got my two little key concepts for the last video up. The flux is this, provided that this dot product, the electric field vector, and the n hat is constant over some area, then the flux through the surface is just A over E dot n hat. I'm sorry, A times E dot n hat. Why did I say over? I don't know. Okay, Gauss's law then is how we use flux most of the time, basically. We say the total flux through a closed surface is equal to the net charge inside. So you imagine here's your closed surface, and this is the net charge inside. So the flux through the surface, total surface, is the net charge inside times 4 pi k, or the net charge divided by epsilon naught. Epsilon naught and 4 pi k are just equivalent ways of expressing the same universal constant. All right. So, excuse me, I just had a Coke and I'm kind of burpy. So what I want to do is look at a couple of examples and show how we use this. And the thing is, it's hard to find cases where you can apply this without having to do the calculus version where you have to integrate. So there aren't a whole lot. And the good news is once you learn 2 or 3 of these little tricks, basically everything is all covered. So first case we're going to take, and this is kind of almost trivial, but I want to show you, is we have a point charge Q. Actually, let me just even do like a point charge with strength Q. We don't know if it's positive or negative. We're just going to say it's Q. Okay? And we want to find the electric field at a distance. So let's say we put this vector R coming from Q. Okay, this is our point charge Q. And at this point here, at the head of this R vector, which is our displacement vector from Q, we want to find the electric field there. So the electric field there is what? Okay, so first, before we even get into this, or get into think about this, we want to look at, and so we know from Coulomb's law what the electric field is there, right? Okay, what I'm trying to do is show you how, if we don't know Coulomb's law, but you know there's this idea of an electric field, that you can use Gauss's law to derive Coulomb's law for a point charge. Okay, so before we get into like trying to find what magnitude it is, let's talk about what direction the electric field has to be in. So if you imagine you're just floating out in space alone, and you see this point charge up ahead. So let's say here's you, okay, and you are floating out in space alone. You see this point charge here, okay. And you have a little meter with you that can tell you what the electric field is. So say it's attached to your head. Say right here, what direction could the electric field be pointing in from your head that would make sense? If it's pointing, this way, for example, does that make sense? And so when I say makes sense, does it? What I mean is, does the symmetry of the problem allow this? So imagine you are looking here at this thing, and you know the electric field vector is pointing upward from your head, and you're arranged like this, so that you're basically facing it. Okay, now suppose you do some little swimming moves, and you take your entire body, and you turn it upside down. Now, you would expect to have, for things to basically be the same, because this point charge is going to look the same. The point charge doesn't have an orientation. It doesn't turn around up and down. So you would expect then that the electric field vector would continue to point this way, or continue to point, up from your head. But yet that means that just by turning around, because see, from this guy's point of view and this guy's point of view, things look the same, right? And yet they both expect the electric field vector to point in different directions this way. So basically what we've shown is the electric field vector can't point up or down here. Okay? Can it point towards the circle, or towards the point? Well, sure, right? Because if this guy sees it point towards the point and this guy is upside down, he also sees it pointing towards the thing. So that's fine. Can it point away? Right. And so what you come out with here, and this is kind of tricky to wrap your mind around sometimes. What you come out with is this idea that the electric field vector really can only be pointing in 2 directions if it's at a distance from this charge Q. It can be pointing straight away from Q or straight towards Q. Which one is it? We're not sure, but what we can do is say this direction, we take the unit vector pointing in the direction of this r vector, and we call that r hat. So we say at that point there's this r hat vector, which has a unit of 1, or sorry, a magnitude of 1, and points in the same direction as r vector. And we can say the electric field here, rather than being completely unknown, we know that it is equal to some scalar number, which we'll call E without the vector hat, times r hat. So r hat points this way. We know that the vector field, the electric field, has to be either pointing in the direction of r hat, in which case, this is a positive number, or pointing back towards the particle, which means this has to be a negative number. So, see, either way, we're covered by this expression, right? We know it has to be pointing towards or away, and this expression works. Okay, great. So, now that we've got that out of the way, we've sort of narrowed down the directions this can point. We want to pick a surface to wrap around this thing, and we want a surface where E dot n hat is constant. So let's look at what the possibilities are. We want, and I'm going to write this over here, we want E dot n hat, sorry, not n vector, n hat to be constant. Okay? So, what are the different ways that this expression here can be constant? Well, there are basically two possibilities. One possibility is that E dot n hat equals 0. And the other possibility, hold on, this will absolutely shock you, I'm sure, is that E dot n hat equals something that's constant, but not 0. Okay, so let's look at these two possibilities. The first possibility is that our surface is that E dot n hat equals 0, which means that if that's true, the E vector and n hat must be perpendicular. And so under what circumstances will that happen? Well, we had the little diagram from the last video where you have your area like that, and you have your electric field going, basically parallel to this plate somehow. Imagine these lines are all parallel to this little area I've drawn. And you can see how the normal vector, which being perpendicular, so if I draw like a side-on view of this little flat area, the normal vector is going to be like that, and then the electric field vectors are like this at various points. Okay, but they all go that way and that way. So if this is true, if these are perpendicular, then we know that the E field vectors must all be parallel to the surface. So that means that the E is parallel. I'm going to use the little geometry class parallel sign to surface. Okay, so what we want to look for is surfaces where E dot n hat is constant, remember. So one possibility is to look for surfaces that are always parallel to the way the electric field vector is pointing. Okay? And so if we look here, what kind of surfaces are going to be parallel to the way the electric field is pointing? And it takes, it might take a little bit of thought, but when you think about it, you'll realize, here's your charge Q, right? What you want is a surface that basically has Q sitting in it. You want a plane that has Q sitting in it. And then you'll see that the normal vector is always going to be, the normal vector is always going to be this way on your surface. Okay? Depending on which way you say your surface is facing. So you could say it's facing this way, you get the same deal. And the electric field vector is always going to be pointing either in or out. Q, right? So these will be perpendicular. So basically we can say that for this to be true for our point charge Q here, we have to have, the surface has to intersect with Q. The problem is that there's no way to build something that wraps around Q from surfaces that all intersect Q, right? Because every single one of these is going to be just like a big, imagine Q is like a tiny little ball. Every single one of these is like a big sheet of metal that comes and slices through the ball. But you can't wrap these things around the ball, because if it wraps around Q, then by definition it's no longer going to be going through Q. So as neat as this idea is, it doesn't work for this particular case, although it will work for some other ones later on. Okay, so to do the there we go. So to do this, we're going to need to look for the case where E dot n is not equal to 0, but constant. And so there are different ways this can happen. One way, which I'm going to show you as for option A, is to have the magnitude of your electric field vector be constant, and have the vector and n hat be parallel. And then E dot n hat, in this case, E dot n hat, since these are parallel, the dot product just means you multiply their magnitudes. The magnitude of n hat is 1. So in that case, E dot n hat is just going to be equal to E. Okay? So, I guess if you want to be formal and make sure we're not, using something different for E, we say it's the magnitude of E. But I'm just using the convention where you usually use lowercase, use, the same letter for the magnitude vector. Whatever. So, now, what kind of surface can we do here where the magnitude of the electric field will be constant? And it doesn't take a whole lot of thinking to realize that the answer is a sphere. Basically, what we want to do is consider, again, if we had our sphere and there were two guys, sort of floating in space near it, and they were both at the same distance from it, then the question is, does it make sense? And so we've already established that they must both feel the electric field either pointing toward the sphere or pointing away. Does it make sense if these guys are both at the same distance from the spheres? So say this distance here is R1 for guy 1, and this distance here is R2. Does it make sense that they would feel different magnitudes of electric field? And if you think about it for a moment, the answer is no, because if R1 equals R2. So actually, I shouldn't have done R1 and R2 at all. I should have done just say they're both their distance R, they're just at different places. Does it make sense the magnitude of the electric field to be different at those two places? And the answer is no. The symmetry of the problem basically says, again, that you'd expect if these two guys basically are the same distance from the electric field and looking at it, they should feel the same field. Okay? So, because it's going to look the same to them no matter which way they're facing or whether they're north or south. They can't tell the difference. Okay, so what we're going to do then is say that we're going to take a sphere so that R will always be constant. I mean the definition of if you want a set of points, a surface that's always the same distance from one point, well, that's the definition of a sphere. So what we do is we wrap a sphere. Actually, I'm not even going to dotted line this. I'm just going to, wow, that's a horrible sphere drawing. Let's see. Let's try that again. Okay. Here's a sphere that I'm wrapping with radius R around Q. Okay. So now what we're going to do is take, and let me get rid of these dudes here. They've been fun, but they've served their purpose. Goodbye. Right. So what we want to do here is we want to take, say, this point here, and we want to check and make sure that this is going to be constant everywhere. So what is E dot n hat at this point? Okay, and we said that we already said that E vector is going to be this scalar E times R. So I'm going to say this is E times R hat dot n hat. Okay, and sent one more over, since this guy is a scalar, we can actually say, and I'm just going to do it this way, is E times R hat dot n hat. Okay, so now which way is R hat pointing? Well, here's our R hat vector. Actually, we know that. Which way is n hat pointing on the surface of the sphere? Well, the surface of the sphere always faces directly away from its center, right? It's always, flat, or the local flatness sort of faces away from the center. So again, think about it a little, and you realize at this point, this is all meant to be at the same point, all these vectors, even though I draw them at slightly different places. But you think about it for a minute, you realize that R hat and n hat point in the same direction. So now, R hat dot n hat, these are both unit vectors. They both point in the same direction. So a vector with magnitude 1 times a vector of magnitude 1 point in the same direction equals 1. So this actually just equals E. Let me fence this off to make sure it doesn't get in the way. Okay? So now we can find the flux over our surface. And this is true for any point, right? No matter where you are, this is going to hold. You'll have R hat and n hat pointing in different directions at different points, but at any point they will always be pointing in the same direction. So if this is your R vector, there's your R hat, and there's your, well, that was more like an N. I'm going to make that N hat, and then I'll make this R hat. Okay? So this is constant all points, which means that we want to find the flux through the entire surface of the sphere. So this equals E dot n hat is just, or E vector dot n hat is just E. We found that. So this term here becomes this. What's the surface area of a sphere? Well, go back to geometry, and the surface area of a sphere is 4 times pi times the radius of the sphere squared. Yeah, right. So it's 4 times the area of a great circle, which is the equator circle. But anyway, okay. So is E times 4 pi r squared, and there is your flux through the surface. The entire surface of the sphere, which means now we are finally ready for Gauss's law. Okay, here's Gauss's law, remember? So, let's take this, go ahead and apply it, and we have this phi here is equal to this, and that is going to be equal to one of these two. So, Gauss's law says total phi, which is equals 4 pi r squared times the magnitude of the electric field, is going to be equal to either this or this, right? We can pick either this form here that has the k in it, or we can pick this form here that has the epsilon naught in it. It's your choice. Now, it's not hard to see that if we pick this one with the 4 pi k, we get some nice cancellation between 4 pi and 4 pi. So, we're going to pick that version. Equals 4 pi k times the net charge inside. In this case, the net charge is just this point charge, q, inside. And so, what this means, I'm going to scroll down just a wee tad so that we have, whoops, that's up. There we go, so there's a little more space. Okay, and let's see, where's the bottom? That's about right. Okay, so what this means then is that these two things equal, right? And what we get then is that that E is equal to, so we divide the 4 pi out, it cancels, and then we're left with a kq on the right side. That gets divided by r squared when that comes over. And there, right there, is the magnitude of the electric field anywhere on this sphere that's a distance r from point Q. And so finally, if we want to get back to an electric field vector, then what we do is, and I will switch to blue here for the grand finale, we just plug that E back into there. So E vector equals kq over r squared times r hat. And right there, we have basically, well, we have, not just basically, we have completely redefined Coulomb's law for electric fields from nothing more than just knowing Gauss's law. So that's kind of a neat result. And I think this sort of shows that Gauss's law can be very powerful, in those situations where you can use it. The trouble is there aren't a whole lot of those, but on those situations, or in those situations where it is useful, it's very useful. So that's Gauss's law in a nutshell. Notice also that we didn't specify whether capital E was going to be positive or negative, but what came out is that it's positive if Q is positive and negative if Q is negative. So you see, we also got the sign convention out of it as well, or the directionality convention for the vector. So that's kind of nice too. All right. Anyway, I've talked enough there, so I'm going to go on to an infinite line of charge, which is an example we also did in class, and then I'm going to go to do an infinite plane of charge, which is probably the big stretcher for you guys. Okay.